Welcome to the E-Pathshala lecture series in computer science. We are looking at the computer architecture course. So, this module is on cache coherence again. It is an extension to the earlier module that we looked at. So, the learning objectives are to discuss about the cache coherence problem in multiprocess and to look at the directory based cache coherence protocol. So, we looked at what is the cache coherency problem in the previous module. So, what you mean by cache coherency is the caches normally support the concept of migration and replication. So, you can migrate data from your main memory and to the cache, that is your migration policy, and the same data can be migrated and replicated in multiple caches. So, when you look at a multiprocess scenario, you can have multiple cache controllers holding the same cache block. So, you have replication of data. Now, in such a situation, what happens is, if one processor modifies the data that is available in its cache, what will happen to the same block that is replicated in other processes? They will have different information. So, that is a coherency problem. So, we have defined the coherency problem in the earlier module, and we have also looked at the Snoop based protocol that is used for handling the cache coherency issue. Now, before getting into the other protocol, the directory based approach, we will spend a few minutes on what is called coherency mess. Remember that we discussed the 3C model with respect to cache optimizations. When we look at modeling cache misses, we said there are 3 types of misses: capacity miss, conflict miss, and your cold start misses or compulsory misses. Now, apart from those misses, when you look at a multiprocessor scenario and you have to handle the cache coherency problem, you also have a 4th miss coming in, which is called a coherence miss. Coherence miss is misses that happens because of the coherence problem. Say for example, you have a cache block which has been read by multiple processors, and if one processor wants to do a write on the block, it automatically invalidates the other blocks. So, when it invalidates this block, when the other processor wants the block again, it definitely only will encounter a miss and it will have to read the block again. So, that becomes a coherence miss. So, now with respect to coherence misses, we have 2 different types of misses here. One is called a true sharing miss and the other one is called a false sharing miss. So, we will see what is the distinction between a true sharing miss and a false sharing miss. A true sharing miss arises from the communication of data through the cache coherence mechanism. Say for example, you have invalidates due to the first write to the shared block, and suppose if another processor reads this, wants to read this modified date block in a different cache, it will definitely encounter a cache miss that becomes a true miss. So, the miss would still occur even if the block size were 1. If you are not looking at block sizes larger than 1, even if the block consists of only one word, the block has, this word has already been modified by some other cache controller processor. So, which means that if some other processor wants to read it, it will definitely encounter only a miss. So, that is an example of a true sharing miss. On the other hand, false sharing misses are those when a block is invalidated because some word in the block other than the one being read is written into. So, basically say for example, I have a block A has been cached by 2 processors. Processor 1 modifies this block, so it has been invalidated there. Processor 2 wants to read this data, he may want to read some other data within the same block. He is not using the modified data that of the first processor, but still because the entire block has been invalidated, he will have to read it afresh and then he will have to use the data. So, that becomes a false sharing miss. Now, this false sharing miss occurs because the block size is going to be more than one word. If the block size had been one word only, then you would not have had this miss. So, the invalidate does not cause a new value to be communicated, but only causes an extra cache miss, because after all I am not interested in the modified word, I am interested only in a different word, but still because the block itself has been invalidated, I will still encounter a miss. So, that is a false sharing miss. So, the block is shared, but no word in the block is actually shared. So, this miss would not have occurred if the block size were only one word. So, that is how you will have to distinguish between a true sharing miss and a false sharing miss. So, this is an example showing a true sharing miss and a false sharing miss. Assume that x1 and x2 are in the same cache block. Process P1 and P2 both read x1 and x2 before. So, suppose if processor P1 wants to write x1, this is a true miss, it will invalidate x1 and P2. It will automatically, because it is doing a write operation, it will invalidate x1 value in P2 by invalidating the block itself. Now, if processor P2 wants to read x2, because the block has been invalidated, the entire block has been invalidated, it wants to read only x2, only x1 has been modified, but still it will encounter a miss. So, it becomes a false miss, because x1 is irrelevant to P2. Similarly, if processor P1 wants to write x1 again, it again has a false miss, because x1 is irrelevant to P2, and when it wants P2 wants to write x2, that again becomes a false miss, because x1 is irrelevant to P2. And if processor P1 wants to read x2, it becomes a true miss, because the invalidate of x2 has happened in P1. So, this is an example of a true sharing miss and a false sharing miss. Now, we look at the problem associated with your Snoop based cache coherence protocol, and why we will have to look at the other coherence protocol. When you look at the Snoop based cache coherence protocol, you know that it has a scalability problem, because the interconnect that you are looking at is a bus. So, if multiple processors try to have access to the bus becomes a bottleneck, and that gives you a lot of problems. So, that is your scalability problem. So, as an alternative to this, can you look at directory based protocol, particularly when you are looking at distributed shared memory architecture. So, the directory based protocol, what it does is, it maintains a directory which keeps track of all the cache blocks in all the processors. So, which caches have copies of the block in the dirty state or clean state, whatever it is, everything is stored in the directory, and information per memory block versus per cache block. So, the positives of that is, in memory it is a simpler protocol, because it is centralized, it is available in one location. The minus is that directory is a function of the memory size versus the function of the cache size. So, depending upon the number of processors you have, number of caches you have, and depending upon the block size, the entire information is going to be maintained in your directory. So, the directory may become a bottleneck. So, if the directory becomes a bottleneck, in order to avoid the directory becoming a bottleneck, what you can do is, you can just distribute the directory itself, you can share it along with the memory modules. So, this gives you an overall idea of what is meant by a directory based protocol. Earlier we have already seen the distributed memory architecture, where the memory is being distributed. It is still a shared memory architecture, but it is a distributed shared memory architecture. So, you can see that the memory and IO are distributed across the various memory processors, which gives rise to a NUMA style of architecture. Now, what we do is, the information about all the blocks, memory blocks, with respect to each of the caches of the processor is maintained in one directory which holds the information about everything. Just like how our telephone directory holds the information about all the details about the customers, here the directory holds the entire information about the various cache blocks, where they have been cached in, what is the status of these cache blocks. But in order to avoid the problem associated with the directory become a bottleneck, you just split the directory and save it along with your various modules. Say for example, if you look at an 8K memory, I am just looking at smaller numbers. Suppose if you are looking at an 8K memory and I have 8 modules here, 8 processors here, then let me say the memory is divided as 1K in each of these processors. I have a 1K memory, and the directory for that particular 1K is available in the first processor. So, the directory for the second 1K is available along with the other processor. So, that is how your directory becomes distributed. So, with respect to the first 1K, the entire information about all the cache blocks in that particular module, that area of memory is going to be available only in one directory. So, it is just one location, but the directory is physically separated and stored in multiple locations in order to avoid the bottleneck associated with your directory. So, if you look at your directory based protocols, the directory keeps track of all the blocks, which caches have each block, what is the status of each of these blocks. It is normally implemented in the shared L3 cache. It can be implemented by keeping a bit vector of size equal to the number of cores for each block in L3. So, depending upon the number of cores you have, it can be maintained as a bit vector. It is not scalable beyond your shared L3 cache, and this can be implemented in a distributed fashion, as I already mentioned. So, if you are looking at the directory based protocol, the basic states of the caches are the same. It is just similar to the Snoop based protocol. So, all the basics that we discussed with respect to our Snoop based protocol hold good here also. Only thing is the way the communication happens. You do not have to send information on a common bus, and all the cache controllers need not keep snooping on the bus, and all the cache controllers had information about their own cache blocks. All that is not going to happen here. The directory is the one that keeps information about all the cache blocks and their status. So, anybody who puts in a request will have to put in a request to the corresponding directory. The directory will respond to the request. But as far as the cache block status are concerned, it is the same as that of your Snoop based protocol. So, a block can be available in a shared state, which means that more than one processor have the data, and we assume that the memory has an up to date information about the data, and you have a set of sharers which is maintained, which will give you the IDs of all the nodes which have shared this data. The second possibility is a memory block has not been cached by any of the processors. So, no processor has this block, so it is not valid in any of the caches. The third state is an exclusive state, where one processor, which is the owner of the block, has the data. Because it has modified it, it has an exclusive ownership of the data. So, the memory does not have an updated copy of the data, and if you are looking at the list of owners, obviously there can only be one owner if it is an exclusive state. So, there is only one owner. So, if your block is available in the shared state, multiple people could obviously have shared it. So, you have a set of nodes which tell you whether they are in the shared state or not. And similarly, if you are looking at an exclusive state, there can only be one owner owning the data, and the memory does not have an updated copy. So, in addition to the cache state, we will also have to track which processors have data when in the shared state. Usually this is maintained as a bit vector by just saying, putting a 1 if the processor has a copy, and putting a 0 if the processor does not have a copy. And in order to make it simple, keep it simple, you can assume that write hits to non-exclusive data can be treated as write misses, and the processor blocks until the access completes. And you can assume that messages are received and acted upon in the order that it is sent. So, we are looking at a message passing protocol here. So, you are not looking at a bus and you do not want to broadcast. The interconnect is no longer a single arbitration point as in the case of a bus. All messages have explicit responses. So, we basically introduce three terms here when you look at a directory based protocol. There are three types of nodes which are involved. One is a local node, the other one is a home node, and then you have a remote node. So, when you look at a local node, the local node is the one where a request originates. So, the node which puts in a read request or a write request is called the local node. So, when you look at a home node, the home node is the place where the memory location of an address resides. So, we have already seen that the memory is distributed among multiple nodes, and the directory associated with that memory is also distributed among the various nodes. So, the node which contains that memory block and the corresponding directory is called the home node. And apart from a local node and a home node, you also have a third node which is called the remote node. But also remember that the local node itself can be the home node. It is putting a request to a memory location within its own directory. Now, a third node is called the remote node, which apart from these nodes has a copy of the cache block either in the exclusive state or in the shared state. So, the remote node can be same as a local node or home node also. Only thing is, if it is local within the same memory area, then you only have to put out intra node messages, you do not have to send inter node messages. So, these are the types of messages that can be passed in a directory based protocol. So, to look at the messages, again recall that we had it is the same concepts that we are discussing as that of your Snoop based protocol. So, the processor can put in a read request or the processor can put in a write request. The request that you put in, it can be a read hit or a write hit. Similarly, it can be a read miss or a write miss. So, those are the possibilities for the processor, and depending on that and depending upon the status of the cache blocks, because the cache blocks can be available in the invalid state, they can be available in the exclusive state, or they can be available in the shared state. So, depending on all these combinations, we will have to look at what activities will have to happen. The only thing that you will have to remember here is the point to point messages that are sent in a directory based protocol. It is not that the address is just transmitted on the bus as in the case of a Snow based protocol, and whoever has to respond to that will respond. Here it is not like that, it is a point to point communication. So, we will just go through these messages one after the other. Say for example, the first message, it is a read miss. So, the processor is putting out a read request, but there it is a read miss. So, the one that is originating this request is called the local node, and the one to which this request is put in is called a home node. So, depending upon the address that the processor has, the processor knows which is the directory for this address, which is the home node for this particular address. So, it will send a message directly to the home directory. So, if it is a read miss, the source of the message is your local cache, the destination is your home directory. So, the format of your message is, it says that this processor wants this data, this block and the address associated with that, and what happens during this for this message is node P, meaning of this message is node P has a read miss on address A. So, it will have to request data and it has to make P a read sharer. Remember that I told you that you have a sharers list. Now, this process is putting out a request for a share operation, read operation. So, this has to be included as part of your sharers list. Similarly, if the processor wants to do a write operation and if it is a miss, again it puts out a write miss. So, the local node puts out a write request to the home directory in the format as P comma A. P is the processor number and A is the address. So, node P has a write miss at address A. So, it is requesting for data, and because it is requesting for data for a write access, it has to become the exclusive owner. Nobody else can own the data now, it is an exclusive owner. Similarly, if it is an invalidate that has to be sent, suppose if you have to do a write operation, before you do a write operation, you will have to invalidate all the caches which have cached this data. So, the invalidate is going to be sent by the home directory. So, when the processor puts in a write request to the home directory knows which are the cache controllers which have cached in this information. So, it will have to invalidate all those cache blocks. So, that is done by the home directory. So, invalidate, a local cache sends information to the home directory at an address A. It says that I am going to write into this. So, the request to send invalidate to all remote caches that are caching the block at address A. So, the directory will have to send in invalidate information. Similarly, the home directory, depending on the blocks that have been cached, the home directory sends in to the remote caches an invalidation of the shared copy of data at address A. Similarly, when you have a fetch operation happening, when you have to fetch the data, the source of the fetch operation is the source node. So, home directory, the source is the home directory. The request goes to your destination is your remote cache, because you will have to fetch data from the remote cache and the address is A. So, you have to fetch the block at address A and send it to its home directory, because the home directory has to cache in that information, and change the status of A in the remote cache to shared, because you fetch the data in response to a read request that has come in from some other processor. So, you are setting the status to shared and you are just giving the data. And similarly, if you have to fetch and invalidate in response to a write operation, the source is again the home directory, the destination is a remote cache, the message it has the address. So, you have to fetch the block at address A and send it to its home directory. You will have to invalidate the block in the cache, because this is going to be modified by somebody else. So, it can no longer be valid. Similarly, when you are looking at a data value reply, this type of message, the message again originates from the home directory, it goes to the local cache and the data is being transmitted. So, it returns a data value from the home memory. Somebody has put in a request for the data value, so you are just sending back the data value to them. So, if it is a data write back, this type of message, again it comes from the remote cache, because the remote cache in response to the directory's request, it is writing back the data. So, the remote cache writes back the data to the home directory, and the address is given and the data is given. So, a write back of this data happens for the address A. So, these are the various types of messages that can happen in a directory based protocol. So, all you have to remember is it can be a read request or a write request that is put in by the processor, and the cache block can be available in multiple states. It can be available in an invalid or uncached state. It can be available in a shared state, which means it has been one or more cache controllers have read in this block. So, it is available in a shared state in one or more processors, or it is available in a modified state in exactly one processor. And remember that the node that puts in the request is called the local node. The one that is holding the directory information is called the home node, and a third node which holds this information either in the cache shared state or an exclusive state or modified state is called the remote node. So, if you look at the directory based protocols from whatever discussions we had, to summarize them again, for an uncached block you might have only a read miss or a write miss, because the block is after all uncached. So, it cannot be a hit. So, it can only be a read miss or a write miss. So, if it is a read miss, the requesting node is sent the requested data and it is made the only sharing node, and block is now shared. So, this is the first cache controller to share that block, read that block. And if it is a write miss on an uncached block, the requesting node is sent the requested data and it becomes the sharing node. Block is now exclusive, because that is the first node that is reading this information and it is doing a write operation on it. So, it now becomes exclusive. Similarly, if you are looking at a block available in the shared state, then again you can have a read miss or a write miss. A read hit is never a problem, you do not have to worry about it. So, read miss, if it is a read miss for a shared block, the requesting node is sent the requested data from memory, because the directory anyway has an updated copy of it, and this is the new cache that is reading that block. So, this node is added to the set of sharers. And similarly, if it is a write miss on the shared block, so somebody else is already holding it in the shared state, you want to do a write operation on it. So, the requesting node is sent the value, all nodes in the sharing set are sent invalidate messages, and sharing set contains only the requesting node, block is now exclusive. Similarly, if you are looking at a block available in the exclusive state and there is a read miss for that block, the owner is sent a data fetch message, the block becomes shared, owner sends data to the directory, data is written back to memory, and sharer set contains old owner and the requester, because it is only a read miss that is happening. So, you can always add this ID to the list of sharers. And if it is a data write back message in response to an exclusive block, the block becomes uncached and sharer set is empty, and if it is a write miss that is happening, the message is sent to the old owner to invalidate his data and send the value back to the directory, and the requester becomes the new owner and the block continues to remain in the exclusive state. So, all this information is again represented in the form of state diagram. So, you have three different states for the cache, an invalid state, shared state and a modified state, and depending on the request coming in from the processor, you have various activities taking place and the state changes happening for your cache blocks also. So, this is a state transition diagram. It is basically similar to the SNOOP based protocol that we already discussed. The fundamentals are the same. So, you have the same states and structure as the transition diagram for an individual cache. So, this gives you the state diagram, directory state machine. So, implementing a directory, implementation issues associated with your directory based protocol. We again assume that operations are atomic, but they really are not atomic in reality, they are much harder to implement. That is one problem. The second problem is the finite buffer sizes that we are going to assume, because you are going to have a lot of messages being transmitted and you have a finite buffer. So, this finite buffer size will also lead to problems. So, when you are implementing a directory based protocol, you will have to take care of these issues. And optimizations, you can look at optimizations again in a directory based protocol also. When you are looking at a read miss or a write miss in an exclusive state, you can send the data directly to the requester from owner instead of first writing it to memory and then from the memory to the requester. But you will have to make sure that you are able to handle the synchronization issues here. And as I already mentioned with respect to our Snoop based protocol, a popular approach is to use a two level hierarchy, where you look at a combination of a Snoop based approach as well as a directory based approach. So, to summarize, we have looked at the different types of cache coherence protocols. We looked at the Snoop based protocol in the earlier module, and this module discusses about the directory based protocol. We also identified what is meant by a true sharing miss and a false sharing miss. Apart from the 3 C's that we have already known as capacity misses, compulsory misses and conflict misses, we introduced a fourth cache miss here, which is called the coherence miss, and we saw how you can distinguish between a true sharing miss and a false sharing miss. We looked at the directory based protocol in detail. The directory based protocol basically helps overcome the scalability problem associated with your Snoop based protocol, wherein the directory stores information about all the cache blocks in all the processors. So, the directory itself may become a bottleneck, because all requests will have to go to the directory first. So, in which case the directory itself will become a bottleneck. In order to avoid that problem, the directory is normally split and stored across the various nodes, and the directory may be distributed, as I pointed out, in all the nodes. And of course, you have implementation issues here also. You will have to make sure that sending of the request, getting the data and the completion of the request, all that happens atomically. That is one issue which will have to be handled. The second issue that you will have to handle is the associated with the finite buffer size of your nodes. So, all these issues will have to be handled with respect to implementation. Similarly, you have certain drawbacks of the protocol also. So, in order to have benefits of both your Snoop based protocol as well as the directory based protocol, you normally have a combination of the two protocols which can be adopted in practical systems. Thank you.